I was going to record these. Just I don't know if you noticed, but I put links to Monday's lecture on the web, and I might as well do that from now on, just because it has all of my pen scratching and stuff all over it. So
It's like a video.
it's it's a video of all of that, and it's not going to have demos. And sometimes I'm going to be talking quietly because I walked over here, and sometimes I'm going to be talking loud because I'm standing here looking right at the. But mostly I'll be loud. Yeah. Part. The elbow is at point A, so that's the joint between two. So there is you could call that a pivot. People generally think of the elbow as kind of a hinge. Two bones come together and they're held together with ligaments, twisted up in various ways and attached, at least two or three of them, I think. So, last chance, get in some sort of an answer. About which point would we find the net torque is zero? Looking for the best answer, by the way. Okay, so this is the beautiful thing about statics, is that you can calculate the net torque about any point that you want to use. And you'll find that the net torque is zero because the angular velocity is zero no matter what pivot point you choose. You can choose any pivot point you want to and look at the angular velocity about that point and it would be zero. So the net torque is zero no matter what point you choose. The reason that's so great is that it lets you be judicious in your choice of points to get to an answer and a discussion really quickly about what's going on. This is a homework problem. So I'm asking you to do this one and turn it in. I told you I wasn't going to give you any hints, but what can I say? Here it is. There's a post right here of mass m, so it's sitting vertical, it's upright. There's a string at the top. This is a silly, complicated thing. A string, not too complicated. A string at the top tied down to the ground. So the string there's a tension due to the string downward. So let me start drawing these things. First of all, the post has a mass m. So F, earth on post. Certainly one thing is that the earth is pulling downward on the post. One object interacting with it. The string is tied up here at angle theta. So there's a tension force by the string. Because it's a string, it can only act along the string, so that tension force is at that same angle theta. And so you can see right away there's two things going on. The earth is pulling straight down, but there's a component of that tension force straight down. So as that tension force gets bigger, then there's more and more force straight downward. And so the force upward, the normal force upward, has to cancel both of those forces, the force by the earth and the vertical part of the string force. So this is the normal force by the ground. And then, so that's the situation that you're given. Now there's a clearly there's a tension force to the left. We supply at height h there a force to the right. It's just called F. Somebody's pulling. Probably a tension force, but who knows?
And there's static friction at the bottom.
It's a post on the ground, so you expect to have friction forces. So there may well be a friction force. You don't know obviously right away in what direction it might be. So what does it tell you? Yeah, it does say coefficient of static friction between the post and the surface is mu. So if you know the normal force, I can say right away that the static friction force magnitude has got to be less than or equal to mu times that normal force. Static friction force has a maximum value. And so whatever the normal force is, there's a maximum static friction force, a maximum, but it could be zero. I don't know because I don't right away know how big these two horizontal forces are. So what do we need? We need, this is a static problem, so the net force has to be zero, and the net torque has to be zero. So how do we deal with the net force and net torque? Well, this is a homework problem, so I'm not going to just write down all the equations. I think what I'd like to do is just tell you what you need to think about. There's going to be two equations for the net force equal to zero. There's the horizontal components have to add up to zero. The vertical components of these forces have to add up to zero. And you're going to have at least one torque equation. There's kind of a nice pivot point. I mean, there's kind of an actual pivot point. You probably think of this point right here down at the bottom as a pivot point. I mean, the thing can tilt over. It doesn't have to. It could slide. So the bottom doesn't have to be a pivot point. The bottom could slip out it could slip out this way. And in fact, if this force right here were applied down at the bottom, you would probably expect that when you made that force there big enough applied down at the bottom, it would just slip out. So there's not an obvious pivot point, but it's in static equilibrium, so we can choose any pivot point we want. A good one to choose, maybe, is down here at the very bottom, because the normal force acts straight through that point, so no torque. The friction force acts straight through that point. I don't know which way friction is going to be. Let's say the force is low enough that it's going to try to pull the bottom of the post to the right, and then I could presume that the friction force is to the left. I don't know that that's the case, but let's assume it is for right now. The friction force acts through that pivot point, the one I chose down there at the bottom. The force by the earth acts through the pivot point. Even the vertical component, the downward component of this tension force, I mean, it's hard to say exactly how it's connected, but it also basically goes right through the pivot point. So none of those pieces, the only pieces that are connected to the only torque at that point is this force right here times whatever the height is, h. That's the part of r that's perpendicular to the force. That's the vertical part. So this height times that force, and the height of the whole thing, capital H, times the part of this tension force that's perpendicular to r. Since r is a vertical line, a vertical vector up to here, the part of the tension force that's perpendicular, so that would be using this. H would be the height r. Sorry, r would be a vector up here of length capital H. And the part of F that's perpendicular to r since R is vertical, that's the horizontal part of that tension force. There's basically two torques. This force here is a clockwise torque. This force here is counterclockwise, and they have to cancel each other. So that gives you an equation with those two forces as the sum of the torque, just saying the sum of the torques due to those two forces is 0. Yeah.
So then the critical height is already h. We have to just solve for h.
So let's get to the let me get to the answer here, or the problem really, which I haven't quite told you, although you've probably read ahead. Horizontal force is exerted on the post. That's shown. Your intuition tells you this force is trying to, well, it works against F, and if it's low enough, you can see that it's going to pull the thing over. The statement here is if the point of application of this force F is high enough, higher than some critical height, then you cannot pull it over no matter how hard you pull, how hard F is. You can't slip this thing out. Now that presumes that the tension force can get as big as you want it to be. That presumes that the force in the other direction, the horizontal component of that, can be as big as you need it to be. However big you need these things to be. But the static friction force is the thing that's limited. You know that if you pull to the right way down here, if you pull hard enough, you're just going to pull that out. Slip it out. You're going to pull harder than the static friction force, and you're going to make it tilt over, basically rotate counterclockwise. So what does it mean? So you can write these equations down, at least one torque equation, at least two force equations. How do you get to a situation like this? And I have a suggestion for you, how you can think about this. At least this is the way I did it. So there's an inequality here. Static friction force is an inequality. That gives you an inequality in one of your, that can give you an inequality in one of your force equations. Force should not be too big, or else this net force will be, well, the static friction force can't be bigger than that. And if you put that limit in, the biggest static friction force that you can get, you'll find out the biggest force that you can pull without sliding it. And any forces that give you a bigger static friction force are going to pull it over, that require a bigger static friction force. Because the static friction force cannot be bigger than the normal force. So let me at least say a little bit about what's going on here, and then I'll tell you what I just did. If you pull harder to the right, what can happen is the tension force, the left component, the leftward component of the tension force, the horizontal part of the tension force, can cancel out this force to the right. If that happens, because the angle of the string is constant, if the horizontal part of the tension force gets bigger because you applied a bigger force, then the vertical part is going to get bigger. It's going to pull harder downward on that post. If it pulls harder downward on the post because the tension got bigger, then the normal force is going to get bigger. If the normal force gets bigger, then the maximum static friction force just got bigger. So as you're pulling harder and harder, all these things are getting bigger kind of automatically. Unless something happens, like, if it's low enough, you're just going to pull it out at some point. If it's low enough, well, I'll let you work it out. But how you show that there's a critical height, so here's my suggestion. You should be able to show that the post won't slip as long as the force you apply is not too big. And what that means is you're showing that the force is less than or equal to something. And at least the way I solved it, I got something like this. The force is less than or equal to some complicated mess you get because, of course, you had 3 equations and you worked out the algebra and you got this. So what does it mean to say that the force can be as big as you want it to be? Well, look at this equation. Down here at the bottom is a number that can get close to 0. In fact, this is 1 minus that ratio minus that ratio. What if I make h, if h is really small, then it's 1 minus some really small number. Okay, it's just some number. But as h gets bigger and bigger, these things, the sum of these two things can get close to 1. And then I've got 1 minus 1. And that's close to that is 0. But I'm getting something as little h gets bigger, in other words, this gets higher and higher, then I'm getting something that's closer and closer to 0 on the bottom here. And that means the force, the limiting, to say that F is less than or equal to this means this is the limiting value of F. And as the bottom here goes to 0, the limiting value of F is infinity, which means there is no limit to F. And so that's what they're asking for, something like that.
So
It's a kind of standard thing to do in physics, to look in limits. And so this is one chance you get to go through that kind of problem. In engineering, you will see other problems like this probably. And if you're a physics major, you'll see a lot of them. Yeah.
So the only thing is, as h approaches h, right? As little h approaches h, that's true that it's 1 minus 1.
Yeah, but it's going to be true before then. Because you're subtracting
Another
this
thing.
part also, and this part depends on mu.
So, but mu over tangent of theta is some fraction. It's not bigger than 1. It can't be bigger than 1.
Mu over tangent theta. Well, we don't know what mu is. It's probably, it could be bigger than 1.
So then it wouldn't matter what h is. It would.
Well, it's going to matter what little h is compared to big H no matter what. This is not about, nobody's going to build this thing and try to knock it over. This is about how to deal with complicated statics problems and what it means to have a maximum, what static friction is. It's a number you don't know, but you do know the maximum value. And then it's about looking at limits. That's what this is really about. So I'm going to give you that essentially as my hint, and these pictures, and then let you do this one. Any questions on? I mean, you can see the kind of complicated problem that's going on here, but yeah.
But if the vertical forces do nothing for torque, wouldn't you only need one force equation to figure out the height? Just looking at the horizontal forces, at the ones that work perpendicular.
Well, that just tells you that the relationship between, that'll tell you the relationship between F and the tension force, but you need the vertical forces too, because that tells you about the normal force, and that tells you about the maximum friction force that you can get. So you have to deal with both vertical forces and horizontal forces. And I'm pretty sure you're going to need a torque equation too, because you have too many unknowns at this point. 2 equations and 2 unknowns is not going to do it. It's not going to get you to something that you need to show this. If you have too many unknowns, then you got to figure out how to write more independent equations. And sometimes you can get away with writing torque, more than one torque equation. Sometimes more than one torque equation will tell you all you need to know. That isn't the way I went through this. I went through it by writing 2 sum of the forces equal to 0 equations and and one torque equation, and I think I just used one. Now I can't remember. Any other questions? Well, I mean, I'm going to let you guys fight through this one on yourself, but by yourself. But I wanted to try to tell you what this was about and some of the complications involved.